Hello, our next lesson is on gas density. So going back to density, density for gases is really no different than densities for anything else. So we learned long ago that density is a ratio of mass to volume. So that's a big V there. It's not mass and velocity, so be careful with that. There is a formula for density derived from the ideal gas law. I don't want you to have to memorize yet another formula though, so this will work perfectly fine. The main difference between the density of a gas versus the density of a solid or liquid is that gases are much less dense than liquids or solids. And so it's not really appropriate to express the density of a gas in grams per milliliter. So rather, densities are in grams per liter. So they occupy a much larger volume per mass than a liquid or a solid. All right, so let's try some examples. First one, calculate the density of nitrogen gas at STP. So we need to know the mass and the volumes. What is the mass? Looks like we're missing everything. We're given nothing really. So what is our approach here? So keep in mind that the density of a substance is a constant at a particular temperature and pressure. And so, meaning the density of a substance is independent of amount. So let's assume you have a certain amount. Let's assume, I don't know, 1 mole. If you assume you have 1 mole of the gas, then that will give you the mass and volume that you need to calculate density. So if you have 1 mole of nitrogen gas, what is the mass of the nitrogen? Well, that would be 28.0 grams. And if you had 1 mole of nitrogen gas at STP, what would its volume be? That's right, 22.4 liters. So for this case, it's as simple as that. So we take molar mass, just in grams though, divided by molar volume, just in liters though, and we get the density of the gas. Go ahead and punch that up. So we get a density of nitrogen gas at STP of 1.25 grams per liter. Now do keep in mind that the density of nitrogen, again, does change with changes in temperature and pressure. So this happens to be just the density at STP. If the conditions were not standard temperature and pressure, then the density would not be 1.25 grams per liter. Example, calculate the density of carbon dioxide gas, not at STP, but rather at 20 degrees Celsius and 107 kilopascals. Now again, our approach is kind of the same. We're going to take the mass divided by the volume. Again, we're going to assume you have 1 mole of the gas. So 1 mole of carbon dioxide gas has a mass of 44 grams. How about volume? What is the volume of 1 mole of carbon dioxide gas at 20 degrees Celsius and 107 kilopascals? There's actually a couple different ways we can do this. One way is we can use the ideal gas law to determine the volume. So let me show that as a separate calculation, then I'll show you another way as well. So V equals nRT over P. So you have 1 mole. Our pressures in kilopascals, so I'm going to use the R that has kilopascals in it, which is 8.31. Temperature 293 Kelvin. And our pressure is 107 kilopascals. Go ahead and pause the video, calculates the volume, and then we'll plug that in. So we get 22.8 liters. So notice that's a little different than the standard molar volume of a gas. Standard meaning at STP. And so again, we just divide these and we get a density of 1.93 grams per liter. Well, I said there's another way that we can do this. So what is the other way of determining the density of a gas not at STP? So again, we take our 44 grams and we divide that by not just 22.4 liters, but remember, 1 mole of a gas at STP has a volume of 22.4 liters. What would be the volume at 20 degrees Celsius and 107 kilopascals? So we're going to do like we did before and determine volume at conditions other than STP. So temperature, 20 degrees Celsius, that is greater than standard temperature. So if the temperature goes up, volume will go up. So we have 293 over 273. And then also apply our ratio of pressures. 107 kilopascals is greater than standard pressure. So pressure goes up, volume goes down. So we'll put standard pressure on top in kilopascals and the 107 on the bottom. Let's do this. Just calculate the volume and we'll do a comparison. Calculate volume and then we'll finish with density. The volume you get is rounded to 22.8, so either way, ideal gas law or ratios of temperatures and pressures. And again, we still get 1.93 grams per liter. All right, so go ahead and try this one. Actually, let's do a comparison. Calculate the density of xenon gas at STP first, and then calculate the density of xenon at 15 degrees Celsius and 1.00 atmospheres. Go ahead and pause and do both those calculations now. So here are our setups at STP. The density is 5.85 grams per liter. At 15 degrees Celsius and standard pressure, what do you notice about the density? So what does that mean? If you increase the temperature of a gas, what happens to its volume? Well, its volume increases. If the volume of a gas increases, what happens to its density? Remember, volume and density are inversely related, so the density will decrease. So when you increase the temperature of a gas, its density decreases. This is how hot air balloons work. You take some air in a balloon, heat it up, the volume increases, the gas expands, and the density decreases, allowing that balloon to float. So maybe useful to know the relationship between the density of a gas at STP compared to not at STP. All right, a little different problem. This time we're given the density of a gas at STP and we're asked to find its molar mass. Now remember, molar mass is the mass in grams of 1 mole of a substance. So we know the density, we know the volume, right? 1 mole of a gas at STP, we know its volume. Find its mass. See if you can do that. Go ahead and pause the video now. So here's a setup. I took the density of the gas and multiplied it by the volume, molar volume to be more exact. Notice that the liters cancel. We're left with grams per mole. So there's probably more than one way of doing this problem. That's probably the easiest way to determine molar mass of a gas given its volume at STP. Now, this is not in the notes, so hopefully you have some space to add this underneath the last example or on the back page of the notes. We talked earlier in the year about mole fraction, or maybe we didn't talk about mole fraction, but I know we did talk about partial pressure. So let's start off with mole fraction. Symbol is a Greek letter chi, looks like an X. Mole fraction is simply a ratio of moles of one substance to the total moles. So when you have, say, a mixture of substances, mole fraction is that ratio of moles. Moles of one substance to moles of all of these substances combined. So let's write it like this. I'm going to write it as, I don't know, mole fraction of A. We take the moles of substance A and divide it by total moles. So it's kind of like a percentage, part over whole, except we don't multiply by 100, we leave it as a decimal. And so mole fractions are always decimals. Now, do keep in mind that's the sum of the mole fractions of all the components of a mixture will be 1. So they do add up to 1, just like percentages add up to 100. In this case, mole fractions add up to 1. Partial pressure. Again, if we have a mixture of gases, each gas has its own pressure based on the number of particles of that substance, and that pressure is known as partial pressure. So what is the relationship between partial pressure and mole fraction? Let's say we want to determine the partial pressure of gas A. We would take the total pressure, that's not pressure of gas T, that's total pressure, times the mole fraction of that substance. So again, it's like a percentage. So if you have a mixture, even mixture of gases, where 50% of the particles are one gas and 50% are another gas, that means that the pressure of each gas will exert 50% of the total pressure. That's kind of how you can think of this equation as well. All right, let's take a look at a couple examples. A container has 1.00 moles of neon and 2.00 moles of helium. If the total pressure is 900 torr, what is the partial pressure of each gas? So let's first find our mole fractions. So mole fraction of neon, we take 1 mole over the total moles, so the sum would be 3 moles. And so the mole fraction for the neon is 0.333. And then helium, do the same thing, moles of helium divided by total moles. And our mole fraction for the helium is 0.667. How about this? What percent of the total pressure do you think the neon atoms exert? Well, 33.3%, I guess. If 33.3% of the particles are neon atoms, it makes sense that the neon by itself would exert 33.3% of the total pressure. So let's take our mole fraction, multiply it by the total pressure, and that will give us the partial pressure of the neon. So we get 300 torr. To find the partial pressure of helium, we could apply Dalton's law. The sum of the partial pressures equals the total pressure. So 300 torr plus the partial pressure of helium equals 900 torr, which would be 600. Or we apply this partial pressure, mole fraction of the helium times the total pressure gives us the partial pressure of the helium. All right, let's have you do one on your own. This one's a little bit different. This time we're not given the quantities of the gases in moles. We need moles. We need number of particles. Number of particles is what determines pressure, not mass. So we have 3 grams of neon, 6 grams of argon, total pressure 120 kilopascals. What is the partial pressure of each gas? All right, why don't you pause the video and work on that now, please. So here's our setup, found moles of each gas first. Interestingly, we have twice the mass, and molar masses are about half that for neon compared to argon. So we end up with a mole fraction of pretty close to 0.5, not quite 0.5. So I just combined all in one step, took moles of neon divided by total moles, that's our mole fraction of the neon, times the total pressure, and we get 59.8 kilopascals for the partial pressure of neon. Again, could subtract that from 120 or do mole fraction for argon times total pressure to get the partial pressure of argon, which is 60.2 kilopascals. All right, that concludes this lesson and this unit. Thank you for watching.